Hello all. In this lecture, we will continue the proof of Lemma 3.3. The lemma says that the type of a linear second order PDE in two variables is invariant under the change of coordinates. For that, we have taken the coordinates, new coordinates as theta and eta, where theta and eta are functions of xy, and we have taken the transformed function w as w of theta eta w of theta eta is equal to u of x of theta eta y of theta eta. And for proving that W is the solution of second order equation of the same type, and now our aim is to prove that W is the solution of the second order equation of the same type. So for that we have applied the chain rule, and we have formed that Ux is equal to W theta x plus W eta x, and Uy is similarly W theta into theta y plus W eta into eta y. And uxx we have obtained as W theta 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 x square theta x square plus 2w theta eta into theta x into eta x plus w eta into eta x square plus w theta into theta xx plus w eta into eta xx. Okay, and we have obtained uxy as uxy is equal to w theta into theta x theta y plus w theta eta into theta x eta y plus theta y eta x plus w eta into eta x eta y plus w theta into theta of xy plus w eta into eta xy. So after this we have discussed in the last lecture, and now we have to calculate uyy. So similarly, which we calculated uxx, we have to find the dou by dou y of uy. What was uy? Uy is w theta y plus w eta into eta y. Again, this contains two terms, and each term is a product of two functions. So here we have to apply the product rule of differentiation also, and this is equal to with respect to y, we have to find the partial derivative. So w theta c into theta y plus w theta eta into eta y. This whole the first derivative of w of theta. This into theta y plus second term will be w theta into theta y plus similarly for w of eta we have w eta theta into theta y plus w eta into eta y in bracket into eta y plus w eta into eta y, or rewriting this we can write it as uyy as w theta into theta y square plus now w theta term. So combining the terms, w there is theta y eta y into w theta and again theta y eta y w eta theta, and we know that w theta and w eta theta are same. So by that we can add the two, so that two terms are similar. So this will be 2 into W theta eta into theta y, theta y eta y, theta y eta y plus again W eta term. What is eta term? W eta into eta y square. Now W theta term, there is only one term, W theta into theta yy plus W eta into eta yy. Okay, these are the all the derivatives of u, first order and second order derivatives of u. Okay, now we have to substitute all these equations in equation number 1. So substituting this in equation number 1. What was our equation number 1? LU, isn't it? Equation number 1 is LU is equal to AUXX plus 2BUXY plus C UYY plus D into UX plus EUY plus FU equal to G. So this was our equation number 1. So substituting this in equation number 1, the equation transforms to an equation in W. W of theta, and instead of x and y, we will get it as the function of theta and eta. Okay, so the transformed equation will be, we are applying the values of ux, uy, ux, uy, uxx, uxy, uyy in equation number 1 where it is needed. So a into uxx term is here, a into uxx. So a into uxx, first we will consider all the terms containing w theta theta. Okay, so a into uxx, we have to multiply uxx by a. So when we multiply this a by a, w, there is a term containing w theta theta into a theta x square. Okay, now in the second term it is 2buxy. So there is the term containing theta theta is w theta theta is will be w theta theta into 2b theta x theta y. And in which one? Uyy. There is a term w theta 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 y square. So it will be c into theta y square w theta theta. So combining all such terms, we can write it as equation number 1 becomes a theta x square plus 2b theta x eta, sorry, theta x to be the term is in uxy. Okay, 2b theta x theta y, theta x theta y plus c into theta y square, this into w theta theta. Now we calculate for the term containing w theta eta. Now the term for w theta eta, what was the term? W theta eta, what will be the coefficient? So here it is w theta eta into 2a into 2a into w theta eta, 2a into theta x. Okay, so the term will be 2a into theta x. So we can write 2a into theta x eta x. Then in the uxy term it is 2b uxy. 2b into theta x theta y plus theta y eta x, isn't it? So 2b into plus 2b. From where we get these two? Okay, that is from uxx itself. So 2a is eta x plus 2b into, in bracket there is theta x eta y, or we can write this in the next step. That will be better. Okay. So plus, now this is in big bracket. Okay. And in small bracket there is okay, 2b into theta x eta y plus theta y eta x plus next term in w theta, that is theta y eta y theta y. So 2 into theta y eta y. So 2c into theta y eta y, which is uxx. Similarly, uyy is same as uxx. When uxx in theta, that all will be in eta, in uyy. Okay. 2c theta y eta y. This whole into w theta eta plus. Now we are going to collect the term containing w eta eta. So w eta eta into, in bracket, the first term a into uxx. So from that we will get into uxx, that is a into eta x square. So a into eta x square, which will be the same as coefficient of w theta theta. Okay, a into eta x square plus 2b, what will be that, eta x eta y plus the next term will be c eta y square, c eta y square into w eta eta plus now there will be coefficients, functions, terms containing w theta, terms of w theta, w eta and like terms. Okay, so that you can write, just I am writing the terms. You have to calculate the terms, you have to verify this. Okay, that is a theta xx plus 2b theta xy plus c theta yy into w theta plus w eta into coefficient is a eta xx plus 2b eta xy plus c into eta yy plus some d into w theta, and from this also we have to rearrange this term theta x plus w eta into eta x plus e into w theta theta y plus w eta eta y plus some f w means we have to rewrite u in terms of w, and f is will be like that. So this will be some capital F. We don't know what the function actually is. So plus capital F w equal to some function of g of theta eta, isn't it? Okay, so this will be the transformed equation, or we can write this equation in a simpler form as LW. By the operator we are using is LW. LW is equal to AW theta theta plus 2B. Okay, 2B, and we know W theta theta, all the coefficient terms contains 2, isn't it? Okay, so we are writing it as 2 into B. 2b w theta eta plus c into capital C w eta eta plus d into w theta plus e w eta plus f into w equal to f into small w. It's a solution. Sorry. F into small w is equal to g. Okay. Where the coefficients of the principal part what is the principal part L naught of small L naught of W, which is equal to A W theta theta, the higher order terms, plus 2B W theta eta plus C into W eta eta. Coefficients of the principal part. This is the principal part of the linear operator L. Of the linear operator L are given by actually we need only this principal part, coefficients of this principal part only we have to calculate, because the type of the equation is determined by these coefficients only. Type is determined by the discriminant. Discriminant is containing only these terms or these functions. Okay, so given by the coefficients are, we have to write it as a of theta eta. What is a of theta eta? A theta x square plus 2b theta x theta y plus c into theta y square. Now b of theta eta. What is b of theta eta? B of theta eta is A theta x eta x plus B into theta x eta y plus theta y eta x plus C into theta y eta y. And the last C of theta eta. C of theta eta is the function a theta x square plus 2b eta x eta y plus c eta y square. Okay. So these are the coefficients of the principal part of the transformed equation, that is the equation in W. Okay. So such an equation and we have to, what we need to show that is this principal part or the type of the equation is invariant. So we need to show that the type of the equation, this transformed equation, will be same as that of the given equation number 1. Okay, and we already told that we can write it as a note. There is no need to calculate the coefficients, no need to compute the coefficients of the lower order terms. There is no need to calculate the coefficients of the lower order derivatives. Lower order derivatives like D, E and F. Since the type of the equation is determined only by its principal part. Since the type of the equation is determined only by its principal part. That is the coefficients of the second order terms. And now we know the functions A, B, C. And look at these equations A, B, C, which is functions of theta, which contains theta x, theta y, eta x, theta y, like that. So from a rearrangement or from simple calculations, we can see that when we consider this as a matrix form, the matrix A, B, B, C. Okay. So this matrix, why we are considering this matrix is because we know what will be the type of the equation is determined by the what, the discriminant. The discriminant of this transformed equation. This is the transformed equation, right? Okay, so what is the discriminant of this equation? The discriminant is actually b square minus ac, isn't it? So here it is capital B square minus ac. So we are writing this in matrix form. Okay, so the discriminant is actually the determinant of this matrix A, B, B, C, and we know the values of these functions. Okay, so writing all these in that form, we can write the right side as a function of, is a product of three matrices. The first matrix being theta x, eta x, theta y, eta y, and the second matrix is similar to the first A, B, B, C in small coordinates, I mean in small letters A, B, B, C, and the matrix is theta x, theta y, eta x, eta y. This you can verify. Okay, so verify that this happens. Okay. So now consider the matrices on the right side. The first matrix, if this matrix if we call it as X, if this matrix is X, then what is the third matrix? This will be X transpose, isn't it? Look at this. The first row of the first X matrix is theta x, theta y, and what is the first column? Theta x, theta y of X dash. So X and X transpose are the two matrices on the left and right of the matrix with the small letters A, B, B, C. And what is this matrix A, B, B, C? These are the matrix of the coefficients of the principal part of the given equation. Okay. Now, and we know this we know as a determinant of the first matrix X, that we know already, that is it was the Jacobian of the transformation. So we denote by J the Jacobian of the transformation, denote by J the Jacobian of the transformation. Okay, then taking the determinant on the two sides of the above matrix equation. So taking determinant both sides of the above equation, what we obtained is above matrix equation, isn't it? Matrix equation we obtain. Here the matrix is AC minus B square. Determinant is AC minus B square, and this is what determinant of theta x, eta x, theta y, eta y into determinant of the matrix, that is AC minus into AC minus B square into det of theta x, uh, theta x, theta y, eta x, beta y. And we know that the matrix determinant of X and X transpose are same. Det of the matrix X and X transpose are equal for the same for any matrix X. Now this is this is the Jacobian J, which is equal to that is det of theta x, eta x, theta y eta y is equal to theta x eta y minus theta y eta x, that we denoted it as J, the Jacobian, and we know that the transformation is non-singular, or it is a change of coordinates, non-singular transformation. Therefore, the Jacobian never vanishes. That means we know that J not equal to 0 for every x and y in the domain. So this is equal to, and this matrix determinant is also J. So this is equal to J into AC minus B square, or by taking minus on both sides of the both sides, we can write B square minus AC is equal to, sorry, J square into B square minus AC, or delta of small l is equal to J square into delta of capital L, the discriminant of the capital L. Now since we know J not equal to 0, since J not equal to 0 and J square is always positive, we can see that the type of the transformed equation depends only on the type of the transformed equation is not depends, or it is same as equation is same as that of the equation 1. Okay, that means if delta L is positive, that means if the given equation is hyperbolic, then delta small l will also be positive. That means the transformed equation is also hyperbolic. Or if it is parabolic, then delta L will be 0. So delta small l will be 0. That means the transformed equation is also parabolic. And if it is elliptic, that means if delta capital L is less than 0, delta small l is also less than 0. That means therefore the type of the equation is invariant. Therefore, the type of the equation is invariant under non-singular transformations. Okay, under non-singular transformations, we have these are invariant, hence the proof of the lemma. Okay, now we can consider some fundamental equations of mathematical physics. Okay, the fundamental equations of mathematical physics are the heat equations, the and um, wave equations, and the Laplace equations. Wave equation and the Laplace equations. Now the homogeneous heat equation is of the form ut minus k into uxx equal to 0, where 0 less than x less than L and t greater than 0. And the homogeneous wave equation is of the form utt minus e square uxx equal to 0, where minus infinity less than or equal to x, which is a less than x less than b less than infinity, and t greater than 0. These equations we will consider later. We will study in detail. Okay, in the later classes. Okay, the Laplace equation, and the third fundamental equation of mathematical physics is the Laplace equation, and it is given by delta u equal to 0, where delta u is dou square u by dou x square plus dou square u by dou y square plus dou square u by dou z square. This is equal to 0. Now you may see that, or you may check that these equations are all second order equations, and we can classify them as hyperbolic, elliptic or parabolic, like that. So first of all we consider the wave equation. So wave equation is utt minus c square into uxx equal to 0. Okay, that is, we can rewrite, instead of a y here, the independent variable is t. So first we write the x, the term containing x. So uxx, so minus c square uxx plus utt equal to 0, which is in the standard form of our second order equation, lu equal to 0. So lu equal to 0, the coefficients were a u, that is the principal part was a u xx plus 2b u xy plus c u yy. So here a stands for minus c square. Here a is minus c square, b is 0, and c, the coefficient of utt, that is 1. So but here there is one more c in equation number, equation in the equation itself, so we call this as some k, let it be k. So our equation discriminant is b square minus ak. So we obtained the discriminant as c square, where c is the constant, that we will explain when we study the equation, wave equation in detail. Okay, so now we can see that the equation is, the discriminant is always positive, therefore the wave equation is hyperbolic. Okay, so the fundamental mathematical, one of the fundamental mathematical equation, wave equation, is hyperbolic. And similarly, you can verify that the heat equation is parabolic and the Laplace equation is elliptic. So the three fundamental equations of mathematical physics belong to the three different classes, and these are the basic equations, and using this the principal part of these equations, we will try to find the solutions of the equations which belonging to the same type. Okay, then one more thing we need to keep in mind, that now if the equation 1 is that is the equation, our standard form lu equal to 0, equation 1 is hyperbolic or respectively parabolic or elliptic, then in a domain D, then one can find a coordinate system. We have already proved that the second order equations remains unchanged or is invariant under the change of the coordinate system, or change of coordinate, the type of the equation is invariant. So we can transform this equation, or we can change the equations into another coordinate system in which the equation has a simpler form. So if the given equation is in very complex form, we can convert this equation into another coordinate system without altering its type. Okay, this is possible by that lemma. Okay, into a simple form, and that form of that equation, if the equation is hyperbolic, then that type of equation has a simple form. Okay, all the equations belonging to hyperbolic has a simple form. That form is known as the canonical form of the equation. Similarly, for parabolic there is a canonical form, and for elliptic there is also a canonical form. Okay. Moreover, in such a case, the principal part of the canonical form, will have a principal part. Canonical form of the principal part may be equal to the principal part of these fundamental equations of mathematical physics. Okay, of the same type. That means if the equation is hyperbolic, then it must have a canonical form which is in the simpler form, and the principal part of that equation, the canonical, which is in the canonical form, must be similar to the principal part of the wave equation if the equation is hyperbolic, and if it is parabolic, then it must be equal to the principal part of the parabolic and respectively. Okay, hence these fundamental equations are of great importance in the study of second order partial differential equations. Okay. Now we will consider the definition of the canonical forms of each type of these second order equations. Okay. So the definition is the canonical form of a hyperbolic equation. Canonical form of a, first we will discuss the hyperbolic equation. Its canonical form is LW is equal to W theta eta plus L1 of W equal to G of theta eta, where L1 is a first order linear differential operator. L1 is a first order linear differential operator and G is a function of theta and eta. Okay. So, if the equation is hyperbolic, we know how to calculate or how to classify an equation, whether it is hyperbolic, parabolic or elliptic. So, now we know what is, if the equation is hyperbolic or not. Now, if the equation is hyperbolic, then its canonical form, that means the simplest form will be of the form W theta eta. The only second order term it contains is W theta eta and the term L1 of W. What is L1 of W? L1 of W means it is a first order linear differential operator. That means it may be a function of theta, eta and W theta, W eta. Okay, these terms. That means in the equation of LU, we know we have the equation, the three principal part plus term function, some d into ux plus some d e into uy plus like that. In the transformed equation, there was some d into w theta, some e into w eta, like that, isn't it? And some f into w. So these all equation, which is a first order partial differential equation, this all represented by this L1W. Okay. So dw theta, ew theta, fw. That part is represented by L1 of W. Okay. So this is equal to G of theta eta. So this is the canonical form of hyperbolic equations. What is the canonical form? LW equal to W theta eta plus L1W equal to G of theta eta, where L1W is a first order linear differential operator. That means L1W represents the first order linear PDE. Okay. First order, understood or notice that it is linear PDE. Okay. So the coefficients of W theta and W eta and W are all functions of theta and eta only. Okay, that we have already discussed in the second chapter. Now we move on to the canonical form of parabolic equations. So the canonical form of the parabolic equation is LW is equal to what? W theta theta plus L1W. Again, L1W is the same as the that in the case of hyperbolic equation. That means it is a first order linear differential operator. So, in the parabolic form, if the equation is parabolic, then the canonical form contains the second order the only second order term contained in the canonical form is W theta theta. Okay, and in the hyperbolic equation it was W theta eta, and here it is W theta theta in the parabolic form plus L1 of W equal to G of theta eta. Okay, now the canonical form of elliptic equation. So this is hyperabolic. Now the canonical form of elliptic equation is LW is equal to W theta theta plus W eta eta plus L1 of W equal to G of theta eta. Okay, That means it contains two second order terms W zeta zeta and W eta eta. But in the case of hyperbolic equation, the other two second order terms, that is W zeta zeta and W eta eta, are absent. And in parabolic equation, the only second order term contained is W zeta zeta, and in the elliptic equation it contains W zeta zeta and W eta eta, but the term W zeta eta is absent. So this you have to study thorough well. You have to study this thoroughly. Okay. Um, so today we can stop here and let's continue in the next lecture. Okay. Thank you. Thank you all.